Good afternoon. It's a great pleasure to be here. I would like to thank the entire AutoCube team for organizing this wonderful conference, and Mirko also for inviting me. My talk will be on exciton charge and spin lattices, if I manage, because I realize that actually the first part of the talk is about their absence in moiré heterostructures. So after this presentation of Jishan, I think there is no need to motivate moiré phenomena for transport or magnetism. Instead, I will focus on moiré twistronics in the context of optical studies involving excitons, where excitons are registry specific. So they pretty much sense the underlying moiré structure or the absence of it. But at the same time, they are sensitive to charge doping as charge is being built up in such a moiré heterostructure, realizing effectively a triangular charge lattice or tagged with a charge spin lattice. So to begin with, I would like to point out that there are actually two rather distinct limits of such moiré heterostructures when it comes to transition metal dichalcogenides. So there are lattice incommensurate heterobilayer systems where you see that the transition metal is the same, yet the chalcogens are different. The lattice constants are different, of the order of a few %, and this is why such moiré lattices emerge without any twist, right? So already at perfect alignment, because of lattice mismatch, we would have this two-dimensional modulation in the interference pattern. The lattice commensurate, marginally twisted homo or heterobilayer, so it can be tungsten diselenide homobilayer, but it can be also a molydiselenide tungsten diselenide heterobilayer. They have very similar or identical lattice constants and at very small twist angles, so if they are marginally twisted, I would like to argue that it's a true challenge to build a true moiré interference pattern that is periodic in space with short and long range order. Instead, there is a very fundamental effect kicking in where the lattice atoms rearrange or reconstruct to form patterns that are unexpected from this notion of PowerPoint moiré. So let me start out with this, and this is a reality that we have seen on many samples. This particular example is a molydiselenide homobilayer at a very small twist angle, and the contrast here in the secondary electron image performed with a standard scanning electron microscope arises from the difference of atomic registries, high symmetry atomic registries in these gray and dark domains. And you see that this pattern obviously has nothing to do with a periodic modulation in terms of a moiré interference effect. The characteristic length scale here is 1 micron, so we see domains of different sizes, and the size varies as we move across the sample. There are very large domains of one exclusive atomic registry only. There are domains that appear in triangular tiling. And obviously for the spectroscopists among you, you will agree with me that it makes a huge difference where you place a laser spot indicated here by the diffraction limit by the red circles. And this is, I think, what contributed to a lot of confusion, but let's understand the origin, the microscopic origin of this lattice reconstruction that results actually in real-world samples of that kind. So because TMDs or transition metal dichalcogenides monolayers lack an inversion center, we distinguish between H and R-type stacking. So H-type anti-parallel alignment or 60, 180 degree twist angle versus parallel alignment at or close to zero twist, right, comes along with a modulation throughout the moiré unit cell, and we see how we move through points of high symmetry atomic registries, labeled here according to the position of the metal over the center of the bottom hexagon. So here in this eclipse stacking, the centers of the hexagons are aligned with respect to each other. In the staggered stacking, we differentiate between a metal residing on top of a hexagon center or a chalcogen residing on top of the hexagon center. So the colors now will indicate the characteristic atomic registries we expect in a moiré cell. If one calculates from first principles kind of the elastic or stacking energy that these registries realize locally, then it turns out that for the two configurations, parallel versus anti-parallel, there is a drastic difference in the penalty a wrong registry would pay, because the layers cannot interlock in the form of a zipper to minimize adhesion energy. So the atoms are simply in place, and there is a global energetic minimum for the HHH registry for anti-parallel samples, and there are two competing for survival, two registries that are close in their energy yet still somewhat distinct. Okay, so what the system tries now is to maximize the adhesion energy at the price of displacing these atoms slightly, right? That comes at the cost of a build of an intra-layer strain energy. And once adhesion wins over strain, right, we have local rearrangement of atoms, and theory has it that actually an ideal canonical moiré system would reconstruct according to this displacement in something that is again periodic, so it's extended in two dimensions, and for the anti-parallel stacking, a hexagonal tiling of reconstructed patterns is predicted, whereas for R-type samples or parallel alignment, there is a triangular tiling of this periodic reconstruction. So note the length scale here, 10 nanometers. This is a characteristic scale of the moiré unit cell in such systems. What we would like to add is a bit of reality, you know, disorder or a point of strain, or in this toy model built by Anwar Baymuratov, what we add is a single rotation defect, so we untwist the sample locally, but we also take into account finite boundary conditions. So this is something that could happen at the tip of such a triangular heterostructure. Energy minimization now predicts that domains of one exclusive registry will grow at the expense of other registries, such that here this yellow or orange region of RHX domain could expand at the cost of the neighboring RHM domain. And according to this global minimum of the HHH registry in anti-parallel stacks, this would be kind of a large-scale energy minimizing nearly two-dimensional domain, because with a growing sample size, these domains can grow to tens, hundreds, and even micron length scales. Certainly the pattern here is kind of random. It depends on the choice of our defects that we introduce. So if we add another rotational defect, so two rotation defects, then the actual result of the energy minimizing morphology will be certainly different. And this is how in a real world sample that is certainly or probably not kind of built by the extreme masters of exfoliation stacking, but this is what reality can be, at least, right? So we see that flake boundaries indeed realize or serve as seeds to quasi one-dimensional type of lines of one and exclusive atomic registries, whereas at the same time we can have bound now by these lines, we can have pretty large domains, 1 to 2 microns, that are of another exclusive atomic registry. So the square here indicates roughly 1 by 1 micrometer, or the optical spot size in a confocal experiment. So what we have done then was to perform actually first hyperspectral photoluminescence imaging at every point of this heterostructure, and correlate with secondary electron imaging, where we expect the contrast, right, to arise from the difference of these registries, to correlate, to have built up one-to-one correlations, and you see that we can clearly overlay the geometry we detect in with optics and with SEM. So obviously, right, and this is what I started out with, depending on the position, the spectral features vary. And the most simple case is actually the photoluminescence of excitons from one exclusive atomic registry, and we identify this registry as HHH by means of many complementary spectroscopy experiments, including the G-factor, characteristic G-factor of these excitons being -16. You see it is a nearly symmetric Lorentzian, or probably Gaussian, emission profile. Yet, as we move away from domains of one registry, for example, into the region where we find what we would call quantum wires, maybe, we find that the G-factor vanishes completely, and the photoluminescence emission would be linearly polarized, and the orientation of the polarization would be collinear with the wires. Then there are regions of quasi-zero dimensional domain network, so what we would call quantum dot arrays. There we recover the G-factor of excitons, but see also the line multiplicity reflecting actually the difference in the quantum confinement of these quantum boxes that have reconstructed non-ideally, non-periodically. And in absorption, one can basically trace these regions and make the same conclusions without going into the details here. So with this insight, right, since we also do chemical vapor deposition of such crystals, and in particular this one is a vertical heterostructure of tungsten diselenide grown on molybdenum. You see that the outer large flake here is molybdenum diselenide, and on top we see tungsten diselenide islands emerging in both H and R type configurations, but also other twist angles I will not comment upon. So the question is, what do we find now with this understanding with this notion of reconstruction on our mind in such CVD-grown vertical heterostacks? In secondary electron imaging, we see that the triangles, typically in CVD-GROW, you obtain very nice triangular monolayer crystals. The triangles are already distorted at the bilayer level, heterobilayer level, and both for H and R type. And then we see that there is an inner core. So this is a zoom to one of the flakes. The reference now that it's H type is to the large edge, to the edge of a large moly flake. And this is still atomically flat. So this inner core here does not reflect a third layer growing. It's just different in terms of atomic registry from the periphery surrounding it. Yes, so a lot of insightful spectroscopy. Let me skip this for the sake of time and share with you our conclusion. We believe that the inner core here of the triangle is nothing else but a periodically reconstructed little triangle, whereas the periphery, and this is something that we confirm optically, but also in high resolution transmission electron microscopy done by our friends in the group of Knut Müller-Kaspari at LMU, we confirm that this is one exclusive atomic registry, so we again have large-scale reconstruction, both in H and R type. Statistics show us that actually, according to our expectation from first principles theory, that actually there is only one registry in H-type that dominates. This is the global energy minimum of HHH, whereas RHM and RHX compete for survival. And remember, there was one. They were not too different, but one would yield the global minimum, and it is indeed consistent with RHM being much more probable upon reconstruction. There are even examples where the domains now alternate between the competing RHM and RHX species as we go across the periphery of the inner core. 2 minutes? Okay. In fact, now I wanted to build lattices, but I'm running out of time. I would like to note that lattice incommensurate heterobilayers are robust against reconstruction, and this is why they really realize something that is pretty close to our notion of PowerPoint moiré. One example is a molybdecyanide tungsten disulfide heterostructure, where according to our theoretical understanding of the system, we have a pretty clear understanding why. Now, in absorption, we observe indeed moiré peaks. There are 3 of them. The multiplicity is due to band folding and hybridization. And we can construct exciton wave functions for all these 3 moiré states, indicating that they are distinct in their interlayer character, but more specifically in the position of the that they reside on the lattice. So this is how a moiré heterostructure builds up an excitonic lattice, right? And the lattice differentiates between the position of the moiré peak 1 with maximum wave function from a moiré peak 2 that is displaced in its whose home is displaced from that of M1. So in such a system, you can imagine now that as we add electrons that will seek the potential minimum of moiré co-localizing with the moiré exciton 1, there is a moiré exciton that can act as a remote sensor of the charged lattice, and having only a minor wave function overlap actually with the electron that we add. It turns out that according to the charging of the system that we have learned to interpret, that this exciton M2, right, that we use as a sensor, will see now a sequential loading of the primary triangular lattice in the monolayer, molybdecyanide, until its mod insulating state, and only then sequentially will the secondary layer, the tungsten layer, charge, such that the system actually realizes a staggered bilayer model with vertically offset 2 sublattices, 1 in moly, 1 in tungsten. And no surprise, and we have seen this in many previous talks, there is emergent magnetism due to correlations of spins residing on this lattice between the nu=1 mod insulating state and the nu=2 insulating state. We see actually quite some variations in the magnetic susceptibility on the lattice reflected by the G factor of this secondary moiré exciton. I see my time is running up, but I would still like to point out the most exotic limit that we have realized today. It's a moiré system in an open cavity subjected to charging. So in the neutral regime and in the charge regime, we see that both excitons, M1 and M2 charged, can couple strongly to a cavity. I should point out that this open cavity has been realized together with Khaled Karay, so it's a brilliant piece of instrumentation where we can now map the magnetism of the spin lattice onto the moiré exciton and couple this into a hybrid mode, hybridize it with a photon, realizing moiré exciton-polaritons with signatures of correlated magnetism. So, Tomasz, I will stop. Yes, here by thanking the group. Most of them are here. Thanking Khaled for the very kind collaboration, and certainly not to forget all other collaborators I will not list, funding, and you for your attention.
So we are quite short in time, but we have time for 1 or 2 questions. So maybe I will ask, so actually these CVD grown materials, how they compare to exfoliated materials when it comes to optical and electronic quality?
Yes, so at the monolayer level, we are probably, these materials are probably not Fourier transform limited, so the line width would be of the order of, between 1 and 2, but rather towards 2 milli-electron volts. The best material would probably exhibit a line width of 1 millieV, but they are good enough to build moiré systems, so they're pretty neat and large scale.